Okay, today we're very glad to have Lauren New as our speaker. Lauren New is a physicist interested in the outsized role of geometry and topology in all manner of materials. She completed her PhD at Harvard University, and then now she is working with Randall Cumming at the University of Pennsylvania on the geometric underpinnings of soft materials, ranging from self-assembled polymer systems to knitted fabrics. Today, she's going to talk about knitting on helicoid scaffold. Okay, Lauren, you can start now. Yeah.
Great. Thank you so much, Hyson, and the rest of the SLAM team for inviting me. This is a great honor. I wanted to talk today about knitting, and in particular, I don't know if you can see my video, in particular, this system. I think knitting now is, of course, like a much more popular topic of discussion among physicists, especially in this area. But I think it's still, there's always a lot more to do. There's a lot of room, physicists, mathematicians, material scientists alike, and just crafters and to play with. Um, and so I hope to share why I think it's a really interesting system coming from someone who knew pretty much nothing about it at the start. Um, I should say this was completed with Geneviève Dion, who runs the Center for Functional Fabrics at Drexel University, which is an incredible center where they actually do knitting and textile work and engineering work on an industrial scale. Like they have machines that, can run for months at a time without stopping. Um, and this really, this would never have been even close to possible without her and her team, um, most of whom actually come from a very different background, but it's been really fascinating to learn, and I've been very lucky to be able to work with these people. And of course, Randy, but you all know Randy. Um, okay, so I'm going to start with a basic introduction to what are called weft knits. They're called weft knits as opposed to warp knits, which is a slightly different kind of knitting. Um, it's a bit of a, but mostly when you see knitting like in your clothing or most people talking about it, they mean weft knits. This is the thing that you do with the two knitting needles. And the way I like to think about it, so here's a picture of, I guess you can see my cursor. I can't see my cursor. It's fine. So here's some pictures of what the stitch structure looks like for the two most basic stitches. These are the first two stitches that you learn when you're learning how to knit um, by hand or by machine. And the way I like to think about it is as these bunny ears, these loops, like a capital omega, where loops are pulled. They interlace with one another, going from bottom to top, and each each loop is pulled from the back of the previous loop to the front of the fabric. And then the next loop gets draped around it and pulled through from back to front. That creates what's called a knit stitch, which is what you see on the left. And the fabric as a whole, zooming out, looks like what you see at the bottom left. On the right side, you have the purl stitch, which is almost exactly the same structure. It's still these bunny ear loops, but in this case, the loops are pulled from the front of the fabric to the back of the fabric, and they're interlaced that way. And so um, you see that if you just switch the crossings, if you think of these stitch patterns as a knot diagram, as a crossing diagram, they're exactly the same structure, except the crossings are flipped. And so this means that knit and purl stitches are really just the mirror images of each other through the plane of the fabric. Um, and in fact, the two photos are exactly of the same piece of cloth, just on one side versus the other side. And also feel free to interrupt. I can't, it's a bit hard to see the chat, but feel free to jump in with any questions at any point. Um, so this already is, even just with these two most simple stitches, I see a hand raised.
All right, that was an accident.
Okay. Um, even with these two most simple stitches, or really in some sense the same stitch, you can already do quite a lot. So first, of course, you see that you get this weird curling behavior in the fabric itself just from a single type of stitch. You make it a little bit more complicated. All you do is, in some places, you replace um, a knit stitch with a purl stitch instead. And so this is something you know as the cuff of your Christmas sweater, where most of the sleeve, this top part, is just plain knit stitches, one after another, arranged in a grid pattern. And then as you come to the cuff, all you do is in certain columns, you replace the knits with purls, and all of a sudden you get very, very different geometry and mechanics both. Even though if you were to look at just the crossing diagram, it wouldn't look that different. Um, and just to give you a sense of how this is done, knitters will know, of course, and I'll talk more about that. Uh, but I didn't realize it was audio. Yes. This is how these fabrics are manufactured in an industrial setting, and it gives you kind of a sense of the loop structure and how they're formed. So what's happening is a piece of yarn is being laid over top of an existing row of these bunny ear loops. And then each needle takes that fresh yarn and pulls it through, in this case, from the back of the fabric to the front to create a new set. And this just goes back and forth over and over again. Um, and with this setup, you can make just purely knit stitches, just one after another, again, in this rectangular grid of stitches. You can get more complicated, where this is exactly that rib pattern that I was showing you earlier on the cuff of the sweater, where you not only have this one row of needles in the front to create knit stitches, but you also have kind of the mirror image set of needles on the back at the top of the screen for the purl stitches. They do exactly the same thing, they're just facing the other way. So you see the purl stitches are created by pulling loops from the front of the fabric at the bottom of the screen to the back of the fabric. Um, and so these two stitches, knit and purl, they really are the bulk of industrial knitting. Um, you can do more complicated things, like you can maybe one of these needles, maybe it doesn't come up to grab the yarn for one pass. And in that case, you can get a tuck or a miss, which are shown in green here. You can also do things where instead of looping the yarn directly on through the loop in the row below it, you actually move it to one side. That's what you see at the bottom left here in pink. Um, and you can play with these and they give slightly different material properties. Um, the fabric gets looser in some places, and you can still keep this. Mostly, you can think of these as like little defects that you put into your fabric. Um, and you can create all kinds of pattern features like the thing that you see in green. Um, or, oh, you can rotate it around in space too. Um, Another thing you can do with knitting that's very commonly done is you can change the layout of the stitches themselves. So not just making the stitches more complicated, like these green and pink things, these still live on, in some sense, a regular grid of stitches. But what you can also do is mess with the grid structure itself, um, by doing things like adding in dislocations, uh, if you're thinking about it like that. Um, in and you can add them in either direction, both as rows and as columns. So on the left, you see that you add a dislocation starting with the red and then going up so that you have more columns as you go up. And you can do something similar with rows as well, where I've added in these wedges of rows in the yellow yarn. Um, And with these dislocations, you can do all kinds of things. You can essentially change the metric of the fabric and use it to do things like make a sock for the Stanford bunny. You can use it to make the heel of a sock, This is, I would say, the most common thing, or to make tapers in like a knitted hat. So if you've ever knitted a hat or you have one on you, you can see that as you go up from the, I don't know, not the brim, the forehead, toward the top where you put the pom-pom, um, you typically want fewer and fewer stitches per row. And so you'll see these dislocations as you go up. Um, and you can do even more fancy things. Uh, it's really a wild and wonderful world of knitting. But what we wanted to start with is, as physicists, we wanted to work with kind of the simplest system that we could, and even just working with knit and purl stitches on a planar grid, on a rectangular grid with no sort of lattice dislocations, you can already do quite a bit. And so this is the system, if you see my video, that we wanted to look at. And this was something that Genevieve, I think, presented to Randy, I don't know, 15 years ago, um, and said, would you look at that? Uh, Here is a material. It's purely made of the two simplest stitches, knit and purl, on a regular grid. You can do this by machine. That's what this is. You can also just knit this by hand. Um, and she had this thing, we called it the magic scarf, where it's this big scarf made out of panels of knitted fabric. And every single panel on this scarf is a different pattern, but every single panel has the same number of rows and the same number of columns. It has the same number of stitches, period. The only difference between these different panels is that is the patterning of knit and purl. So within this rectangular grid of each panel, I have a different selection at every point. Is this point knit or is it purl? Uh, and that's it. And from that, you get this incredible zoo of uh, of different materials with which, as you can see, have very different geometries. They also have very different mechanics as well. But it's all done on the same machine continuously with the same yarn. So can we explain just this? And then the bottom right is just kind of showing you, as intricate as these patterns are, if you kind of flatten them out on the table, they all end up looking just like a bunch of knit and purl stitches. Um, oh my God. I didn't realize there was audio to these videos. Um, So, of course, uh, we've all been trained. Oh my God, that's a metamaterial. Oh my God, this is a soft device, a soft actuator. Um, Really, I think to me, what's most incredible about this is that it's just this material with uh, very remarkably tunable properties at a coarse scale that all come from the same underlying yarn. And, you can get such a broad range of material properties that, material scientists may only dream of. Um, and you can do this very robustly. So on the left are some patterns that you saw from the magic scarf. There's a face that with a nose that pops out and eyes that are set back that Chelsea and John B have made in the knitting lab. Um, of course, you can get, you can make a knitted spring, which is just a, a piece of knit and purl that are next to each other. And, it has some springiness, which is relatively independent of the yarn properties themselves. You can also have patterns that have multiple stable equilibria. So you can pull it out and then all of a sudden you get a different stable pattern. And I just want to impress upon you that these are extremely robust features, right? You can wash these, you can dry them, you can use them for years and years because they're encoded in the topology of the stitches themselves. And this happens at the time you manufacture the fabric. You don't have to do any extra like steaming or treatment or anything. Um, this will just, these patterns will show up and they'll work and they'll persist for a very long time. This is also relatively material independent. So these these patterns were made on using all kinds of different yarns. The top is a gray one, which is really a copy of this olive thing. Um, and it's made out of a nylon yarn that is not actually very stretchy. It's about as stretchy as like sewing thread that you would put, in your sewing machine or use to like stitch up a button. Um, the middle is a slightly stretchier wool blend, and the bottom is a cotton thread. You can make this out of fishing line. You could make it out of, wet spaghetti or cooked spaghetti if you really wanted to. Um, and you would expect to see roughly the same kinds of patterning come out of the same kinds of stitch patterns, the same layout or instructions of knits and purls. And so this suggests that we can understand this patterning through the stitch shape and its geometry and topology um, in a way that's independent of the specific yarn mechanics involved. Um, right. So our question is, how does this work? Um, are there any questions so far? I know that was a lot if you guys aren't used to knitting, but
Maybe I'll ask a question on purpose this time. There seems to be a rectangular lattice assumption built into this. Is that universal?
uh, it's not necessarily universal. Again, you can have a different, like you can put dislocations in your lattice, but there is maybe one thing I'll just point out is that knitting is fundamentally composed of these loops, and these loops have to rest on something, otherwise you can just pull them out. And so, for instance, this top left loop, this red thing, um, it's holding up the blue loop. If it weren't there, the blue loop, you could just pull it out, and then you could pull out, in fact, all of the loops on the left. And so there is this kind of constraint that a stitch, whatever that means to you, um, is essentially one loop holding up at least one other loop. And so there's some kind of dependency in like the graph of loops in your fabric. Um, and a rectangular structure gives you a nice way to do that. Every loop is dependent on the loop underneath it. Uh, and that naturally gives you a rectangular grid, but you could imagine, well, I can't, but maybe you could, uh, some other kind of structure that where all these loops can be held up by each other. Does that answer your question?
Yes, yes, thank you.
Related to that, you just mentioned that every every loop depends on the other one. So how do you deal with the boundary one?
Yeah. So what actually happens is on the left side, let me see. Can you see my cursor?
Yeah.
So on the left and right edges, what you do is you just connect these up. That's no problem at all. So here you could connect these two, and then you go around, and then you connect these two. And that's how standard machine knitting is done and hand knitting. That's not really an issue. At the bottom and the top, usually you start out with something a little bit different. You could naively just thread something through each of these loops in a way that prevent them from being pulled out completely. And any solution like that will work. Uh, Knitters actually tend to do something a bit more fancy, where they put this loop, they 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 hook it over this one hooks over this one, and so on down the chain, and then the last one you tie off the last one, something like that. But as long as those are taken care of, it's not usually a problem. And in fact, in the physical system, you can actually get away with not managing this at all. Uh, if you're depending on what fabric you're working with. Sometimes the friction of all these crossings is enough to hold things in place um, for a lot of applications.
Thank you.
Um, Okay, cool. So, right. So our question is how does this thing work? What can we explain about it, starting from the stitch level, and hopefully getting to the fabric level if we have time. So I'm going to zoom in first on the structure of individual stitches, individual loops in a knitted fabric. Um, I'm going to talk about what was termed the helicoid scaffold. This is something that Mike Tanis, who's actually an artist, and worked with Randy on questions about origami and kirigami, came up with. Is the story goes he took this thing on the right and said, "Hey Randy, look at this," one day. Um, so I'll tell you what you're looking at. So the structure of these yellow and pink yarns, so that is the structure of a knitted fabric. And the surface that they lie on, you'll see, is a set of helicoids that are kind of glued together in the middle. And what this separating surface does is exactly that. The pink yarns lie on one side of the surface, and the yellow yarns lie on the other side. And so it naturally, uh, so first of all, the yarn path in 3D lies along this very beautiful surface. But also, this surface keeps yarns of adjacent rows from actually touching each other. The surface has two sides. You can continue it in space. And it gives this nice way to think about kind of parameterizing the path of the yarn. So what does this actually tell us in terms of physics? So this is a slightly cleaned up picture. And I'm just going to point out a couple things. So yarns, I keep losing my cursor. That's fine. So this is the same thing again, just orange and blue yarns this time instead of yellow and pink. And each knitted loop, each of these bunny ear loops, they span two helicoids. They're two helicoids wide. And each helicoid, you'll see as you go from left to right, alternates in chirality. And this lets you nicely glue them together in between. And the knitted stitch naturally lies on a left and right helicoid that are next to each other, whereas the purl stitch on the right naturally lies on the opposite-handed combination, a right-handed helicoid next to a left-handed helicoid on its right. And so this fits together well for just a single type of stitch, like a knit or a purl fabric. But the question is then, okay, that's nice. But what happens when you join these two kinds of surfaces and yarn paths together? And for that, uh, I'm actually going to step back a bit. So just thinking about this helicoid surface from this slide. So what does this surface remind you of? It reminded Randy of the Schwartz-D minimal surface, which is this big orange thing. This is a triply periodic, it's a minimal surface. It has two sides, so it divides space into two pieces, and it has cubic symmetry. And one way to think about this complex surface is you look at it from the top down, and what you'll see is that it looks like a diagonal checkerboard of left-handed and right-handed helicoids that are all smoothly connected together eventually, but you look down from the top or from the side and you'll see, and you cut out a little core of it, and that core will be a left-handed or right-handed helicoid. And so this suggests a nice way to fit these helicoids together, and you take one slice of it that gives you alternating left and right-handed helicoids. And that's what we call this helicoid scaffold surface that the knits sit on naturally. And you can also look at, you can take this one diagonal slice with left and right-handed alternating helicoids, and you can move that plane forward and back. And what happens then is you go from left, right helicoids to right, left helicoids. And this gives us a perfect way to connect knit stitches with purl stitches. So let's see. Yeah, so this is, see, on this diagonal slice, you could fit a bunch of knit stitches on this subset of the D surface. And looking from the top down, so you can put your knit stitches there on a left-right helicoid pair. And then if you wanted to transition to a purl stitch, you need a right-left helicoid pair. And to do that, you can either go forward in the plane or you could go back in the plane. And so this suggests that when we transition between knits and purls, just going back to a normal knitted fabric, we have some choices to make. This suggests that when we put knit stitches next to purl stitches, that they're going to be offset slightly in the plane. And this is exactly what you see. So this is what you saw earlier in the cuff of the knitted sweater, where the knit stitches stood out and the purl stitches were kind of set back. What this construction doesn't tell you, though, is, at least topologically, whether the knit stitches should be in front of the purl stitches or the other way around. The one thing that does discriminate this is we go back to just basic geometry, and it turns out these two options are a little bit different. So on the left, you see two ways to put a purl stitch next to a knit stitch, with the purl either being in front or behind the plane of the knit stitch. And it turns out that the one on the top takes less yarn. So if you're knitting under tension and then you release that tension when it comes off the machine or comes off the needles that you're working with, what will naturally happen is to minimize the length of the yarn. The purl stitch is going to end up sitting behind the knit stitch. There will still be this planar offset, but it's going to choose to order itself this way. And that is what you see in a knitted fabric. If you have a sweater, you can see the knits tend to be in front of the purl stitches.
Is there a smooth path between those two options?
I'm sorry?
Is there a smooth path connecting those two options?
Not on the Schwartz D surface. You have to kind of violently rip out, because you have to take helicoids that were next to each other and rip them apart. But the helicoid is just kind of a tool to think about the yarn paths. And so when you take it out, yeah, the yarn path, of course, is always continuous.
But maybe along the same lines, can you have you thought about also the shape of the knit and the purl? So given that you have this now nice parametrization and by an energetic argument, what curve does it actually trace out on the helicoid? Does it have
Yes.
geometric interpretation?
Yes. Well, so the helicoid, I guess it's nice in that it gives us already this smooth picture, for the smooth surface upon which we can put the yarn path. I don't think we've studied too closely, like, if you were to if you were to wiggle the surface very slightly, what that would change about the yarn path, and then like energetically what that would mean. But that is actually kind of next on the docket, is to kind of add in those modes and then see what they do to the yarn path energetically. And if that's something that is a better picture than the one I'm going to talk about in a minute, or how the full fabric tends to deform. I know that's not really answering your question. but yes.
No, that's good. Yeah, thank you.
And so this gives us a sense that when we do these knit to purl interface changes, already something kind of weird is going on. On the right side, you see what's happening with when the interface is not just left to right, but from top to bottom. And it turns out the preferential plane change direction is actually flipped when the interface is horizontal instead of vertical. And in this case, the purl plane likes to lie in front of the knit plane. And so you get this weird thing where you compare these two pictures, these two photographs next to each other. Sometimes the purl is on top, sometimes the knit is on top. And what that leads to is very weird transitions between knits and purls. So this is if you have horizontal and vertical interfaces. If you arrange them, this pattern that you wouldn't think is chiral, K's along the main diagonal and P's on the off diagonal, but you end up with this kind of staircase pattern around the center point. And so even though these loops themselves aren't really chiral as a whole, they have these chiral pieces that Mike Tanis pointed out. They lie naturally on two adjacent helicoid surfaces that have a handedness. So these parts of each loop do have a handedness, and they interact in different ways based on how they're placed next to each other in the stitch pattern. And even weirder things happen when you have like diagonal interfaces, but again, on a lattice grid, we're only interested in either horizontal or vertical neighbors. Yes, Dan.
Does that mean you could get the opposite handedness with like a half unit cell offset to the interface?
Yeah, exactly. Yeah, it's very weird, but that's okay. I don't want to open a whole thing, but yeah, this is something that I think Mike Dmitriev and Lizzie Dresselhaus are very interested in terms of, when you're talking about the symmetries of these structures, of knit purl structures, how they're arranged, what pieces of the stitch actually contribute to kind of the fundamental domain of the thing. Yeah, it gets very weird. But that's so this at least was our understanding of just basic knit and purl stitches next to each other on a rectangular grid, how they interact with each other kind of around this fabric plate. So okay, so now I'm going to zoom out a bit and talk about going from that picture to a much broader picture of the fabric itself as a continuum, because on this magic scarf, like, yes, these plane changes are happening, but that doesn't really explain just how three-dimensional this resulting pattern is. And so how do we get these much larger curvatures that end up creating a lot of the mechanical properties at large scale? So, looking back at just a knit structure or the purl structure in terms of the yarn crossings, could you stare really hard at this yarn path and then realize, oh my God, the fabric is going to have these large scale, long wavelength curvatures? Maybe you see it already. But I will point out, of course, first that a knit fabric, this is back from the very first slide. If you were to cut out a piece of, old t-shirt, maybe one that you got from the March meeting, those are usually plain knit structures like what you see on the left. And what happens if you cut out a little rectangle of it is it will actually roll up quite tightly. And if you cut out a large enough patch, what you'll get is the top and bottom rolling in towards you and the sides rolling out away from you. And normally you don't notice that because the shirt is nicely hemmed and everything, and it covers a large enough area. But if you were to make rags, out of old t-shirts, you see this effect immediately. It's very strong. So why does it do that? Why does a knitted fabric with this kind of yarn path with all these loops, why does it curl like that? So our thinking, very broadly speaking, is again, this shouldn't really depend on the exact material that the yarn is made out of. It should come from the structure of the loops themselves. And so what we noticed is that we actually found this out because we were drawing so many different like knot diagrams for the yarn crossings. And every time we would always draw the loops in, a bunch of overlapping loops, but we would always get confused which way the crossings should go, which yarn should be on top at every crossing. And it turns out the way to remember is that I know this picture on the right is red and blue, which is confusing, but this is all knit stitches, purely knit. And so all the loops are pulled from the back to the front of the fabric. And what you see is that at every crossing, they're all pretty much coherently oriented. So the more vertical yarn is always the one on top at every crossing. And that means that at every crossing, it looks something like this Pringle thing on the left, where the yarns, they have some thickness, they probably have some bending modulus, and even if they don't have a very high bending modulus, maybe they have some tensile modulus. That means, they want to minimize their length, and they can do this by not bending very much. But in any case, at every single yarn crossing, you have a yarn on top and you have a yarn on the bottom, and they have to get out of each other's way. And in order to do that, of course, they have to bend out of the way of each other. And for whatever reason, bending modulus, tensile modulus, whatever you like, they want to oppose that bending that's been placed upon them by the constraints of the other yarn. And so, the mechanism is kind of unclear at the microscopic level, but if you believe any part of it, what you get is that at every crossing, you get a little tiny 2D curvature moment. And if you add these up, so in the knit fabric, all the crossings look like this. And so when you zoom out to the fabric scale, you end up with a huge, oh gosh, screen just died again. Is that you end up with a field of curvatures. I'm going to reshare. Oh, too excited. You end up with a field of curvatures, one in the X direction, one in the Y direction, that this fabric wants to obey at the large scale. So you get double curvature, you get Gauss curvature, or at least a tendency toward it at the microscopic scale that shows up coherently at a large enough piece of fabric. And of course, the other
Lauren,
ingredient, yes,
can I ask a quick question over here? So
yes.
you make a very nice argument for the sign of the curvature as being negative, and the opposing saddle-shaped geometry. Can you say, or say if you have thoughts on at least the simplest caricature of this picture, if I understand, will predict that you have uniform curvature, especially uniform if the stitch pattern is the same, right? Is there any thoughts, or do you have evidence for variations of curvature, even if the stitch pattern is the same, potentially because tension is not the same everywhere?
So, sorry, just so I understand, we're still talking about just purely knit
Yes,
material.
purely knit, like the picture you
Mhm.
have. If the tension in all the filaments is the same, then then I would imagine then yes, the the reference, the curvature that it wants to have would be sort of spatially homogeneous, and as you described, saddle-like. Are there situations where you see that potentially the tension is not maybe because of friction? Because if you have friction, then the force balance might lead to tension in homogeneities, even if this knit pattern is the same, in which case then you can have, even for the same knit pattern, a potentially spatially varying curvature. Is that something that you can see?
Yes, yes. And this is something every knitter ever has seen.
Okay.
So, I mean, because the simplest example, I mean, the closest to home I would say is that if you ever tried to knit yourself with the two needles and just create, like the end of a scarf with just purely knit stitches,
Yeah.
if your tension is uneven because in some places, I don't know, you were more anxious
Mm-hmm.
or or at the beginning you didn't know what you're doing, you'll see that reflected in the shape and the curvatures of the fabric. And some people actually do this for fun.
Yes.
Is they'll see, okay, on this day when I was knitting, you know, I was stressed out about this thing and there, my stitches looked very uneven
Tighter.
and this part
Yeah.
was tighter.
Yeah.
I don't know. I think manipulating this on a large scale, like on purpose, is
Yeah.
I don't know how robust that would
It,
be.
do the machines allow you to vary this, or is this harder?
They do, they do. They
Okay.
let you set different kinds of tensions.
Okay.
In principle, you could set whatever tensions you want as the yarn is being laid down. Um, there are a ton of engineering issues that yeah, are I think honestly very underappreciated. But yeah, and generally, of course, it's not like, usually it's you turn a knob with
Yes.
different numbers on it. Who knows what that actually means, besides, some monotonic uh change in tension. But yeah, and it's something that's extremely important in practice is making sure that tension is even and managing it. Uh Absolutely.
Okay. Okay. Thank you.
Yeah, thank you. And thanks for all the questions so far. This is great. Um, okay, so yarn crossings. From the yarn crossings, we have some sense. Okay, there should probably be this Gaussian curvature happening at a large scale in the fabric, at least for a region of coherent um, knits or coherent purls, because that's just the mirror image of the whole thing. And of course, the other piece is, well, I've put in Gaussian curvature to my surface, to my fabric. But I want to remind you that that's competing with this flat metric of the stitch layout itself. Again, this rectangular grid of knits and purls, which, you would expect to roughly be the same size. They're made out of the same like bunny ear loop configurations. Sure, they have slightly different 3D structure, but, there's no reason why we would expect purls to take up, that much more space than knit stitches. And so the fabric as a whole, if you think about it as a surface, as a thin surface, you should think of it as having a relatively flat metric, where I could take this thing and I could lay it out in the plane, and I don't actually have to stretch any of the loops to do that. I may have to uncurl parts of the fabric, but that's not the same as actually stretching it out, and creating like large tensions on the yarn itself. And so, if you agree with that, at least, then we have a problem because we have this desire for Gaussian curvature in the material alongside a flat metric. And this is something that Gauss, in his remarkable theorem, pointed out, is that you can't actually have a surface that does both of these things, that has a flat metric and also has non-zero Gaussian curvature. For exactly the same reason you can't make a flat continuous map of the surface of the globe that like lies flat on the table without distorting any kinds of areas. Um, so this object as a whole is therefore something that experiences large-scale geometric frustration. So these two pieces fight with each other. And so we know, of course, this happens in any thin and soft surface that can bend and it can stretch, is you get this competition between the Gaussian curvature and in-plane strains. And so we were like, okay, well, we've done something like this before, modeling, the growth of surfaces and films and skins. And so this is something we can directly apply to the knitted fabric, at least as a first pass. So our model is lifted directly from a lot of recent work in that area, where we say, okay, I think of this fabric as just a flat elastic sheet, like a sheet of rubber. And the only difference is that in some parts of this rubber sheet, where I have knit stitches in red, I'm going to enforce, oh no, I'm going to enforce that in these red areas, this rubber sheet wants to have the double curvature of the knitted fabric, where there's a positive curvature in the y direction and negative in the x direction. And in the purl, it's going to want to do the same thing, just with opposite sign curvatures. And I let these two terms, I let this energy equilibrate, and I figure out what kind of deformation of this rubber sheet gives me the lowest energy at the end of the day. And just by doing that, just by giving it a picture of these red and blue regions on the sheet where it wants to have different kinds of curvatures, we can roughly reproduce the patterning that you get in this entire scarf. So I think all of these patterns are here somewhere. And you can see, so this is what we got from simulation in the second row, and then the photo of the actual physical sample at the bottom. And so, of course, it's a rough approximation. It doesn't actually incorporate a lot of those little details about like these planar offsets that I told you about. I know it's kind of a tease. That is something that would be really fun to incorporate down the line. But in terms of capturing these bulk curvatures that contribute to a lot of what's going on in the scarf, and give it such dramatic shaping in 3 dimensions, this actually does relatively well. There is one tuning parameter in this, which is, I call it thickness. It is thickness for a true elastic sheet. Of course, that's not really what we're dealing with. It doesn't have, a fabric obviously doesn't have the same microstructure there. But what it does capture is some sense of importance, of relative importance between, how willing are individual stitches and loops willing to stretch in the plane of the fabric versus the fabric bending at a similar scale or a larger scale. So with that one tuning parameter, and it actually doesn't matter so much exactly what it is, but this one gave us the best results. So there are a couple things I want to point out. I know I'm a bit over time. Somebody yell at me if that's an issue. But a couple things that I want to point out about this system, because it's actually quite subtle. This is, self-folding, and it's got all this structure, and it has a flat metric. But this is not the same as origami systems. It may look like it. In fact, in some places, it really does look like, oh my God, there are like actual creases and folds in the material. But I want to make it very clear that this is not the same thing. The 3D patterning that shows up in a knitted fabric is not putting in folds where I know exactly where the folds are. In fact, the folds are something that emerge from the broader curvature distribution. it's not something that, for instance, at this knit purl interface, anytime I have one of those lines, that's where a fold is. That's not the case at all. In fact, in this Mura-Ori pattern, in the red and blue, you can see the knit and purl pattern, and you can see their interfaces. But in fact, the fold lines that you see on the right actually occur purely along vertical and horizontal directions. And it's not something that you would have necessarily expected just by looking at it. And they tend to occur, these, where you see large curvatures in the resulting fabric, they tend to occur in the bulk of a knit or a purl region. I hope that makes sense. And the other thing about this is that, it's very unlike origami in the sense that it's not really locally predictable, at least not immediately. With origami, I know that I will have a region, I will have a curvature singularity along this line where I put in a fold. And so I know at least locally that's what it will do in the deformed configuration. In this case, it's not quite the same, just on a predictive level. So here are two different patterns. They're very similar, except in one case, these squares are shifted by like one stitch or one or two stitches, like a tenth of the scale of the square itself. But even that little change gives you very, very different singularities and curvature for the resulting fabric. That at least, you or I think looking at this wouldn't necessarily be able to predict in the final pattern. Yes.
Hi, could you actually show us one, like maybe like the Mura-Ori or something where, like, can you open it up to show like where the folds are versus where the pattern changes?
Oh, yes. So that, in fact, you can kind of see it on this slide. I can do the video, but it's a bit harder to see. You can see if you look at where the folds are indicated on the left, you can and you kind of squint at the middle image, you can actually see the fabric is kind of deformed there from being in the quote folded state for so long.
I see.
Does that help?
Yeah. I was just confused because you said there are straight lines and I don't really understand where those straight lines would be.
Yeah, it's really it's really hard to predict. And what I'll say actually to that point, I may skip, I'm gonna skip this. I just want to step back and say that, so I've given this, a very similar talk to actual knitters, like knitting circles and things. And I actually, I have a bunch of slides for them where I give them a pattern and then I say, what will this fabric do? And then they know immediately, oh, these ones, okay, maybe these are kind of easy. I show them this pattern, they're like, oh yeah, it'll come out in like a peak like this. And that's exactly what it does. And even this one, they'll know. And it's always very remarkable to me because this is something that, in simulation, even in kind of the dumbest continuum model, it takes, quite a bit of power to do the global optimization that's required to figure out where these curvatures that minimize the global elastic energy will actually end up in the surface. So even though the local rules are simple, how they combine and interact with each other to form these final patterns to get the global energy minimum is quite complicated. But it's something that apparently, if you're a real knitter, it's something that there is a logic to it. That's something that I think is very exciting in itself because, of course, we can do this computation and do it in a very dumb way, but I think there's a bit of a middle ground still to be understood about what are they picking up on about these patterns that do emerge, even if they're not exactly locally predictable. I didn't subject you guys to this, but yeah, I highly recommend, of course, if you're at all interested in the system, to literally just start to play with it. It's very beautiful, very rich, and again, this is only barely scratching the surface of what knits are capable of. And again, not just, for our clothes and sweaters, but like at an industrial scale for materials that are actually functional. They've already proved that part of them, but so yeah, so this is, I guess, my conclusion. But I do want to just emphasize that this was all possible because of this intuition and, domain knowledge that was honed over a very long period of time. And it was very evident, like in the knitting lab, this is where it came from. And even just our very basic model came from sitting around and playing with this and trying to knit it and taking, trying and failing many, many times. And just lots of play involved. So hopefully I gave you a bit of a taste for that. And yeah, I would like to answer any questions you guys have. Thank you so much. I hope my thing just said 2 o'clock, so.
Okay, so we can still have time. We can extend it for about 10 to 15 minutes.
Oh, sorry.
Yeah, it's fine. The time is totally good. So now we have questions from I think James, the first one.
Yeah, hi, that was really great. Thank you. My wife's a knitter, I'm not, but I was really fascinated with your last comments because it's consistent with what I see with my wife when she's knitting, that she knows just from practice and intuition and having repeated things and learned things, what's going to be the result of different combinations of knitting and purling and other things that she does. But then you make the point, which is the point that we all engineers ask ourselves, is where does modeling improve, the situation? Of course, we're engineers, so that's what we do for a living. We model so that we can design jet engines and so on. This is something different where the human being is intimately involved in the product. And I'm wondering, from your understanding, you're obviously a knitter and you're also a scientist and an engineer. Where, in your opinion, is the interface between learning and using what you've learned because you're intelligent, you repeat things and you see what the results are and so on, and actually modeling to try to improve whatever it is you're trying to improve? I'd be interested in your comments on that.
Oh gosh. Well, thank you. I don't so I should say, so I knew nothing about knitting before I started this project a couple years ago. And so I'm nowhere near like, I wouldn't even call myself a knitter because just literally because I haven't spent that much time with the craft itself. Uh, what I'll say is that knitting in particular, I think we're very lucky to find people like Genevieve and others, um, already approaching this like with an engineering mindset. What I'll say about knitting in particular, kind of as compared with a lot of other, um, similar forms, is that what's great about it is that it's already industrialized. And so if there's something we learn about it, even just a little tiny bit, if there's something that can be made a tiny bit more efficient uh, or anything like that, it's already ready to be deployed at huge scale. And that's something that I think makes it very exciting compared to a lot of other material technologies, which, are incredible feats of engineering, but aren't necessarily industrialized yet in the same way. And so that made it all very
Yeah.
exciting. Of course, we we don't necessarily have anything to offer them right
Yeah,
now,
yeah, yeah. Well,
but
I guess I was thinking, the idea of minimizing energy and so on is commonly used in engineering, and you brought that up as one of the states that define the equilibrium state and so on. And I'm
Mhm.
thinking, well, okay, if the objective is to minimize the amount of yarn that you're using, if that's what a knitter naturally does, they want to minimize the amount of yarn that they're using because it costs to buy yarn and so on, then they will learn over time to do certain things to reduce the amount of yarn that they're using. On the other hand, you can develop a mathematical model. You really didn't go into the mathematics as much as I thought you were going to go, but let's say that you did. And then the objective was to minimize the amount of yarn that you're using, but still make, pleasing sweaters and so on, visually looking sweaters and so on. I just find it interesting, this interface between the human brain and what we regard as pleasurable or pretty or lovely or whatever, and the mathematics behind it, which we can use to increase or reduce certain things. And anyway, this is maybe something you could talk with your colleagues about, but I find that aspect of this quite interesting.
Definitely. I'm a huge that's why that's I don't have not much to add off the top of my head, but that's kind of why I wanted to end on this note that like the craft and the human exploration of it, by hand, I think is extremely powerful and it's something that, I wish we could tap into more, not just with this system, but with everything we do.
Right. Anyway, thank you.
Thank you.
Daniel?
Hi, Lauren. Great talk. I'm wondering, so this preferred curvature that's encoded, this saddle-like one, is there a knit pattern that already exists or that you can cook up that allows you to do preferred curvatures which are cylinder-like instead, or even have positive Gauss curvature? Or are we always going to be restricted to saddles of different orientations, basically, and having only that to play with?
So if you believe this extremely naive picture that I presented here, uh, the answer is as long as you can figure out a yarn path that encodes these types of, this array of crossings with these orientations, then you should be able to do whatever you want. And I think there is some evidence of this, and specifically by Mike Dmitriev at Texas A&M. He was studying uh, chainmail, where you have rings and they're linked together in different ways to form essentially a fabric. And so they have different kind of ensembles of crossings. And if you're clever about it, you can make different arrangements of crossings that give you, I think, positive Gaussian curvature as well as the negative ones here. So that's the first thing I think of. I hope there's more work on it, but I'm not sure.
Okay, thanks.
But with knitting for sure, this is because of the structure of the loops, this is kind of like a divine coincidence that uh it works out so coherently nicely. But yeah.
Thanks.
Dimitrios?
Hi, Lauren. How's it going?
Oh, hey, what's up?
Great, great. Excellent talk as always. I have a super silly question to ask. So, what would happen if I put like a closed loop, an actual knot somewhere, just at this location or something more cute? Or if I put a line of them, for example,
You mean like way back?
like way back, I think where you had this slide with the different things that can happen. Is it just at this location? This is what happens if I put a closed loop? And would it matter how I close the loop and how many times? Yeah, that I think that's pink thing is kind of like what I'm thinking about.
Yeah. I'm not entirely sure about you mean like if I just put, if you think of these as heads, if I just dropped a necklace onto one of these heads and
For
closed it?
example, for example, so you have different knots, right? Depending on how you loop them and so on. There's a whole
Mm-hmm.
and if you had like a whole scarf, it's actually probably not even an actual knot because you can pull it apart. You can just
Mm-hmm.
pull one thread and completely unravel it. And I was wondering if you maybe have thought about what happens when you put these closed loops, and if it matters what type of loops you put, how are they, you know?
Yeah, I would say just based on my guess is that unless you're working at a very small scale, loops being closed is not actually a huge deal.
Okay.
In practice, these systems, things like friction and just other like other yarn interactive effects take over way before any kind of topological, any kind of like real global topological uh effects, right? Like, so the topology here is extremely important, but um, only kind of in a local sense.
Okay.
So about closed loops, I'm not sure that would, I mean, unless there's something, you know, the loop being closed is on the scale of like another stitch. I'm not sure I envision something, you know,
Mm,
fundamentally different happening
interesting.
there.
Thank you.
But yeah, that's a good question.
Cool talk.
Okay. Are there any other questions? Okay. Yeah. Timothy.
I have a quick question. Sorry. If you can say a bit about your conclusion slide, Lauren, on emergent connections in addition to emergent curvature.
Um, oh, where did it go? Emergent connections. Okay, hang on. Uh-oh. My slides quit on me. Oh, just kidding. Also I saw there was another question, but
Oh, yes, yeah.
I'll read it to you in a second. Um, blah blah blah. Oh my gosh. All right, let's try this again. Aha. Oh yeah. I I don't, at least not without thinking about it a bit more, mean like a technical connection. Um, I guess what I mean is that as you of all people I think well know that these curvatures interact with each other. These curvatures that emerge even on a large scale, uh, like low energy, will talk to each other. Um, right? They're quite uh, they're quite closely coupled, right, with one another, just talking to each other through the geometry of the surface. I think that's all I really meant by this.
Okay, but maybe then on the same point, you all your examples had, because you switched from knit to purl, and so you have discontinuities in the reference curvature.
Mhm.
Do you see either in the simulations and or in the actual fabric, what's the structure across that boundary?
Mm.
What does the fabric do and what does the simulation do?
Yeah, so right, so I kind of told two disjoint stories, right? Because the simulation, the red-blue simulation, doesn't actually encapsulate this planar offset thing that I kept going on about, um, that we understand from the scaffold picture. So, how to actually do that, I don't know. Um, of course, it's I think it's what complicates it is that right, this continuum picture relies on kind of waving away a lot of things about the microstructure and only assuming that, right, it happens to have a sense of large scale uh modulus, right? It's whereas what happens at these interfaces between knit and purl at the smaller scale, that's something that's very much at the scale of like the thickness of the material of the fabric itself, or like that's very much a microstructure question. And so I'm not actually sure how to combine them in a principled way, other than that I can tell you that they both are very apparent. If you have ideas, I would love to know.
Great. No, I was just curious if you saw some distinctive sort of potentially boundary layers. And yes, it would depend on the effective thickness and the lattice spacing of the knit and purl structure. But I was wondering if there are classes of how you continue of patterns of deformations of how you continue from knit to purl that depending on the overall architecture, maybe there's categories of this boundary layer behavior that you could try to see from the continuum picture and then ask microscopically what features, how they potentially connected.
I see. So off the top of my head, I don't know, but I would like to think more about this question, especially in the sense that if you can get something kind of, more mesoscale, like even if it's only heuristic, this understanding, again, that right, like knitters seem to have, I think that would be right, that would be like the gold, in my mind. And this is something I remember Demetrius, like we also talked about a bit before. Yeah. So I don't know, but I would like to know.
Fantastic. Thank you.
Yes.